Good afternoon. This time we'll do a flight following normal ops to see how the various systems are used during a flight. We'll also climb close to the ceiling to see the pressurization system in full load. Plus, we'll fly at Mach 0.9. We're the only payload in the plane, so we're quite light today. Go ahead and go through the flow.
Okay. Standby power, test and armed. Because the normal DC circuit is opened, the red light shows that the standby power circuit is actually closed and providing power. It can provide electrical DC power for 30 minutes to an hour, but only for most flight essential systems. Batteries on the bus. ACAS on. This engine indication and crew alerting system is a display system showing engine parameters and warning messages. Fuel booster pumps should stay in norm. This gives the Saitek control over the electrical boost pumps. When I press engine start, the pumps will be engaged to provide that first light up with a consistent fuel flow. When in norm, the pumps also turn on when low fuel pressure is detected or when cross-feeding is in effect. This little monster is equipped with an APU. The APU is a small jet engine placed in the tail that can power a DC generator and can provide pressurized bleed air for engine start and the environmental system. This little turbojet spins at 60 to 70,000 RPM and provides about 110 horsepower, sustaining a 400 amp DC generator and 50 psi air delivery pressure. I don't know why, but the exhaust temperature always goes above the max EGT indication.
Oh, that's because the panel shows continuous operation values, not startup maximums.
Even though the APU generator is rated for 400 amps continuous, there is a 300 limit imposed for ground ops, as 400 would heat up the inner coils to unsafe values. The deck is heating up under the scorching sun. I'll use the APU to cool it down. Avionics can go on. APU generator load goes up. The inertial navigation system can go to align. This system needs an initial position to align to that is taken from the GPS and inserted via the CDU. For redundancy, there are two independent inertial systems. It's time to close the doors. I'll set up a departure and an arrival at Constanza. I'll choose an eastbound departure and a westbound approach. We cannot do flight level 510. We have 75% fuel, so that loads us quite a bit. Great. The INS have aligned. And that's the pre-flight flow completed.
Good. Now start the engines.
The two Rolls-Royce AE3007C are two-spool, high-bypass turbofan engines. Two-spool means that the fan in the front spins at a different RPM than the core of the engine. At max thrust, the fan can spin at 8,700 RPM, while the core will spin at over 16,000. The high bypass feature means that more air goes around the core than enters it. After the fan, more than 80% of the air actually moves around the core, and less than 20% of it is enough to power the cycle. This bypass air is the one generating the big bulk of the thrust force. The engines are of the mixing type, which means that the bypass air and the hot and fast core air mix up before exiting the exhaust nozzle. The advantages of a mixing turbofan include high-speed thrust efficiency, noise reduction, low drag, and simpler reverser geometry. The FOTEC is powered by the DC circuit while the engines are off. When they go online, the FOTEC is powered by a special embedded generator. This assures normal functioning and control even if the entire electrical system fails. For startup, a jet engine needs a threshold pressure of the air inside the combustion chamber before inserting fuel. That pressure can be achieved in two ways. One way it can be achieved is through electrically rotating the compressor until it reaches a certain RPM, which assures airflow and compression in the combustion chamber to get the cycle going. The second way is to use a special starter turbine that is linked to the engine compressor. This latter option is the one used for the Citation 10. The APU injects air into the 14th stage compressor. That means it rotates the second spool directly, while the first spool is indirectly linked to the overall engine regime. In the case of the 3007C, the FOTEC takes care of everything. You don't need to be careful when you insert fuel into the engine because you don't have direct control over the fuel nozzles. The FOTEC senses the right amount of airflow and inserts fuel at the right time. For the PT6A, you had to hold the condition lever until at least 13% rotation. Moving that lever would directly inject fuel into the combustion chamber. Too low of an airflow, and a hot start condition would fastly develop. We have good start on both. 570 Celsius at the turbine, 22% N1 meaning 1914 RPM at the fan, and 64% N2 meaning 10,318 RPM at the compressor level. Before the taxi, we should check the controls. Make sure that the upper rudder flap doesn't move when flaps are up. flaps for takeoff. First detent is a slap position. The second is flaps 5. Here we go. Taxiing to runway 18. We're going to take the runway half length and backtrack all the way to the numbers. Testing brakes and reversers. One of the advantages of a mixing turbofan is the simplicity of the reverser. Because all thrust producing air can be found in one place, the engine only needs a single bucket to scoop that air for reverse thrust. That is in opposition to a separate float turbofan, which needs at least 2 scoops to take bypass air and re-energize it with core air. I'll enter the runway here and backtrack it to full length. I have to say, the Citation 10 taxis like a GA aircraft. It's very responsive, though it needs some power to make it move.
Do you know that you are paying upwards of $7,000 for an hour of flight in this aircraft?
Yes, but do you know that the two engines provide about 6 tons of force at takeoff? And did you know that being a gas turbine engine, the AE3007C is favoring exhaust velocity on top of all other parameters? However, the temperature, pressure, and velocity is smaller than for the -66D. So how can it generate more power? The secret's in the flux of air it processes. While the -66D throws 3 kilograms of air per second at 600 knots, the 3007C throws over 100 kilograms every second at 500 knots. That is a massive increase in momentum. And that is the secret of turbofan and turbojet engines. They inhale huge amounts of air without massive increase in internal pressures or temperatures. To tell you the truth, there is no advantage in mileage. However, if we normalize to maximum takeoff weight between the TBM and the Citation takes it all. That is because even though it burns more fuel per mile, given its speed and weight, it is a more economical solution for companies that do long flights with 6 passengers. Not to mention that turbofans exhibit a leaner power depreciation over an altitude range. Takeoff power set. I forgot to set the initial altitude on the flight guidance system. Now I'm telling the autopilot to climb while the system has a descent in mind. Well, first-timers make mistakes. The auto throttle is obviously wanting a descent because of that zero target altitude. And then I realized the problem. I'm seeing it's not climbing at full power, so I switch to flight level change. This mode pushes the engines to max climb power and then maintains speed by pitch inputs. I'll also set the easterly heading over the Black Sea. I can shut off the APU. And now, the ECS. The system takes air from the 9th compressor stage, and in low thrust regimes, the 14th stage. The system is still manual, so I have to select the right cabin altitude to satisfy the outside air pressure. As we're going to flight level 450, I will select a cabin pressure of about 6,600 feet. As we're climbing, to check the current ceiling I can achieve, I can go to the CDU and check the performance data page. Currently, we can climb to flight level 470. During the climb, whenever I consider the climb rate to be too low, I can change the climb profile in the CDU. We were doing 0.90 climb, but normally this aircraft does a Mach 0.80 climb in the upper atmosphere. That will ensure a faster climb rate. The ECS is keeping 8,000 feet. Should be about 6,800. Just as in the other pressurized aircraft you've flown, you can customize the target cabin altitude to be on the edge of the maximum differential pressure that assures adequate oxygen for you and the passengers. This pressurization is weird. It could happen from a faulty outflow valve, but I saw it can repressurize if need be, so that's not the problem. Okay, we're coming in for landing. Took a westbound arrival and the RNAV approach. In the Citation, I have a fully coupled VNAV calculator. This system is integrated in the FMS and delivers the correct vertical profile to the flight guidance system. Not only that the auto throttle keeps the correct speed, but also the autopilot keeps the correct vertical velocity to stay on the profile. It takes most of the workload from the pilot and puts it in the flight manager's lap. My job is to customize the flight stages to my liking and then watch the plane fly them. Well, this actually adds a bit more stress on the crew because you have to be way more miles ahead of the plane. In usual flights, the pilot should be at the arrival gate when physically at the departure one. To aid the electrical and ECS systems, it's best to start up the APU. In case of emergency, it adds another redundancy layer.
sink. Don't 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 sink.
And I forgot the thrust levers in a high thrust setting. At the moment of auto throttle disengagement, it'll go to high thrust and ruin my touchdown point plans.